Here's a quick video on how to report numbers in scientific notation. So the purpose of scientific notation is to write really huge numbers or really small numbers in an easier format. It only makes sense to use it when you're trying to report numbers that have lots of zeros, either at the beginning of the number or at the end of the number. So for example, let's take the diameter of the sun. The diameter of the sun is 1,390,000,000 meters. All right, so that's a really big number, and there's a lot of zeros, and you have to kind of count the zeros to see how many there really are. So an easier way to write this and an easier way to read it would be in scientific notation. So this would be conventional notation. Now, if I were to write this in scientific notation, it would be I'll just show you what it looks like first, and then I'll explain how to do it. 1.3 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 9th. 10 to the 9th. So this exponent up here tells you exactly how many digits are in this number. So you don't have to go counting you have to count to write it, but for the reader, it's a lot easier because you know exactly how many digits long is this number, how big is it exactly. That's what the exponent tells you. And you always have to put your units at the end. So that's the diameter of the sun written in scientific notation. You can also write the size of something very tiny using scientific notation. So for example, if I were to write the size of COVID, which is a virus, the size of COVID is 0.00. This is approximate. It's approximate size. There's 6 zeros. I had to look these up, of course. I don't have this off the top of my head. Meters. That's the diameter of COVID. And this is conventional notation. So I could write that in scientific notation as 1.0 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, negative 7th meters. And that's scientific notation, which I'll just indicate it by SN stands for scientific notation. Okay, so you can see that it's a little bit easier to write. There's not as much to write, and it's a little bit easier to interpret because I can say, okay, there's 7 digits here. You know, this is 7 points past the decimal. So that tells you something about immediately how small it is without having to count how many zeros are at the front of this number or how many zeros are at the end of a large number. All right, so now let's get to figuring out how to write. So how are you going to write numbers in scientific notation? So this is how you write. This is basically the rules for writing something in scientific notation. So first, look at your number in conventional notation and then rewrite it with only a single digit to the left of the decimal point. So I'm going to write my example in red here. So let's just take a really big number like, we'll just make one up, 407 trillion. Okay, so there's thousands, millions, billions, and trillions. Okay, right, because this is, okay, 1,000, million, a billion, a trillion. Okay, so 407 trillion. That's conventional notation, which I'll write with CN. CN means conventional notation. So I'm trying to rewrite this number. I'm not trying to change the number because this is a measurement for something. Maybe this is the distance between the Earth or the Moon. I mean, it's not. I'm just giving examples. You've got some kind of something that you've measured, the distance between two things. Maybe this is trillions of meters from here to the moon or whatever. I'm trying to rewrite the same number in a different way. So I'm not trying to change my number. So first I'm going to rewrite it as 4.07, but I'm not done yet because obviously 4.07 meters would be different than 407 trillion meters. Those are two different numbers. So we're not done yet because 4.07 doesn't equal 407 trillion. So now my next step is I have to keep going. The next two steps are going to be about making 4.07 equal to 407 trillion. Step 2, multiply your new number by 10 to some unknown exponent. Now, just giving you some foreshadowing, step 3 is going to be about figuring out what that exponent is. But again, I'm just taking you step by step here. So let's go back to our example. Our new number was 4.07, and we're going to multiply it by 10 to the x. Okay? We don't know what the exponent is. I'm just using x as a stand-in. All right, so let's move on to step 3. Step 3 is going to be about figuring out what is the exponent, what value should x take. Figure out what exponent, that's like what value for x, will make your new number equal to the original number in conventional notation. Because again, these two values should be equal, just written in different ways. To figure out what the exponent needs to be, it's going to take 2 steps. So we'll have 3a and 3b. First, we need to figure out how many places must the decimal place move if we wanted to move it back to the original position. So our new value is 4.07, and we want to make 4.07 equivalent to our original value. So what was that? It was 407 with how many zeros? So 3, 6, 9, 12, followed by 12 zeros. So I'm just going to write these 12 zeros here. 3, 6, 9, 12. Okay, so if we want to make 4.07, if we want to change it back to 407 trillion, we would have to move the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 spaces. And then put it there. Okay, because our original number was 407 followed by 12 zeros. So this now would be 407 followed by 12 zeros. So 14 spaces. This is now going to be the value of our exponent. So count these jumps. That's the value of our exponent. So the value of our exponent is now 4.07 times 10 to the 14th. Now there's one more thing that we have to check, and that is which direction did the decimal point have to move? We moved the decimal point to the right. That means the exponent is positive. But if we had to move the decimal point to the left, it would create a negative exponent. So basically, if your original number is greater than 1, the original number meaning the one in conventional notation up here, your exponent in scientific notation is going to be positive. If, however, your original number in conventional notation was less than 1, like something like 0.0001, then your exponent in scientific notation will be negative. Because negative exponents make tiny numbers, and positive exponents make large numbers. If you moved decimal right, positive exponent. If you moved the decimal left, it will be a negative exponent, because that would mean your original value was a tiny number, less than 1. I'll show you an example of that after this. So we had to move the decimal point. If you look up to the example we used here, we were changing 4.07 back into 407 trillion. We moved the decimal point 14 spaces to the right. That tells us we can keep our exponent up here positive. So 407 trillion equals 4.07 times 10 to the 14th. This number down here is the same number as 407 trillion, but written in scientific notation. So again, just to recap, There's a single digit to the left of the decimal point. So you rewrote 407 trillion as 4.07, but then you multiplied it by 10 to the 14th to make it equal to 400, because obviously 4.07 is much smaller than 407 trillion. That's why you need to multiply it by 10 to the 14th, which is a 1 with 14 zeros after it. So these two values are the same number, just written in different ways. All right, so let me show you how you would do this with a very small number. So let's say our number is very, very tiny. We're talking about a particle size, something smaller than a virus. So let's say our number, it's got a lot of zeros on the front end instead of the back end. So 0.00000. We just have lots of zeros, 25 meters. Now this is some kind of a measurement of some kind of particle, tiny particle, and I want to rewrite this in scientific notation. So remember step 1. Let's go back to our steps. Step 1, look at the number in conventional notation and rewrite it with a single digit to the left of the decimal point. This number has no digits to the left. I mean, there's zeros, right? But we're ignoring those zeros. We need to write a non-zero digit to the left of the decimal point. So we're going to write it as 2.5. Okay, 2.5. Now, 2.5 is a lot bigger than 0.000000025, right? So these two numbers are not equal yet. We need our number in scientific notation to be the same value as the number in conventional notation. So we're not done yet. So we need to multiply by 10 to the x, 10 to some exponent. We don't know what that exponent is yet. So how do we figure that out? So this was step 2. Remember step 2, multiply the new number by 10 to the x. That's what I did there. And step 3 is to figure out what the exponent needs to be. What exponent will make our new number in scientific notation equivalent in value to the original number that was written in conventional notation? So basically, how are we going to make 2.5 the same as 0.00025? What does the exponent need to be to make these two values equal? So step 3 tells us how to do that. First, how many positions must the decimal in our new number move to get back to the original number? Okay, so let's look at that. So how many zeros were in our original value? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there were 9 zeros at the beginning this time, not at the end. So there were, let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah. 3, 4, 5, 6, 7, 8, 9. So we want all of these zeros to be between the 2 and the decimal point. So we need to move the decimal point all the way back. What is all the way back? How many times do you have to move it to get all the way back to the original number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this was step 1. This was step 2. This is now step 3. We're writing this as 2.5 times 10 to the 10th, right? But remember, that's 3a. 3b is looking at which direction you moved the decimal point. So let's go back to our instructions. Which direction did the decimal point have to move to change our new number back into its original value? If you moved the decimal to the right, the exponent is positive, but if you move the decimal point to the left, you have a negative exponent. This time we moved it to the left, right? We moved 1, 2, I'm moving to the left here. I moved it this way, left. So that means we have a negative exponent, okay? Now we're done. So we have, step 1 was a single digit to the left of the decimal point. That's the 2. So only the 2 goes to the left of the decimal, and 0.5, okay? Then step 2 was we multiplied by 10 to some exponent. Step 3, we figured out what the exponent was. So 3a was how many places did we have to move the decimal point to get from 2.5 back to our original value in conventional notation? It was 10. And did we move it left or right? We moved it to the left. That means the exponent is negative. So The reason the exponent is negative is because our original value, the original number in conventional notation, was very tiny. It was less than 1. So that means that the exponent has to be negative. If it was greater than 1, the exponent would be positive, like in our first example. And it's equal to 0.00000000025 meters. Same value, one's in scientific notation and one's in conventional notation. So that's how you write a number in scientific notation.